Next chapter, differentiation. Now, in calculus, we will be working with many types of functions, and one of the major things we'll be interested in is how these functions change. The ideas here are very intuitive, and you may actually have come across them already, but unknowingly. Looking at a graph of a function, we will see some places it increases and in other places it decreases. Knowing how a function increases or decreases tells us about the behavior of the function, but it's still not sufficient for other uses. In mathematics, differentiation is the transformation of a function into its derivative. The derivative of a function for a particular value is a measure of either the rate at which the function is changing at that value or the gradient of the function at that point. Here are two functions that are both increasing, but one is increasing more rapidly, and that's because it looks steeper. But how steep is it, and why does it increase more? We need a way to describe how rapidly the function is increasing or decreasing. If these two functions were straight lines, it would be a lot easier. When working with lines, we can use slope or gradient to describe how quickly a line is increasing or decreasing. By taking change in y divided by change in x, we can describe the increase by giving these ratios of numbers. So the graph on the right is increasing more because it has a larger slope. How about our functions? They are not straight lines, and so we can't use slope to describe how they are changing. The way to do this is our first subtopic: average and instantaneous rate of change. Now, when it comes to instantaneous rate of change of a function, the goal is to describe how a function is changing. The difference between instantaneous and average change is that we want to describe the change using only 1 point and not 2 points. The problem is, when we want to describe the rate of change of a function, we often need 2 points. This is so that we can record both the change in the y direction and the x direction. If we are at a single point, it doesn't seem like we are changing in either direction. If you use the formula on a single point, this will give us 0, which is really not useful in describing change. But there is a way of finding the rate of change at a single point. In fact, we use the average change, but in a different way. To approximate the change at a single point, we begin by choosing the point along with another point. This makes it 2 points. Using the 2 points, we find the average rate of change between them. But we don't stop there. We start moving the second point closer and closer to the first one. Each time we do this, we record the new value for the average rate between them. As we find these values, they will become closer and finally settle at a specific value. This is called the limiting value and works great as an approximation for the instantaneous change of a function. Let's look at a simple example to see how that works. This is a function, and we want to know the instantaneous rate of change at this point. We take it along with another point. We measure the average rate of change between these 2 points using our formula. And if we do that, we get a value of 1. Now let's move that point a little closer. The average value now is 1.5. Moving closer, this time the value is 1.8. So as we move the second point, we are getting different values for the rate of change. Even though they are changing, they seem to be getting closer to a limiting value. In fact, they appear to be getting closer to the number 2. We continue moving. At a point really close, our average value is now 1.99, and that is really close to 2. So we can conclude that the limiting value is 2. Since we are looking at the average rate and moving the point closer, 2 can be considered an approximation for the instantaneous rate of change of our function at that point. In other words, it gives us a perfect way to describe how our function is changing at that single point, which is exactly what we want. Actually, you will realize that If the point came as close as to be at the same exact point as our original point, then the straight line will only touch the graph at one point. Such a line is called a tangent to the curve, and the point at which it touches the curve is the point of contact. And so the instantaneous rate of change at a point on a curve is the gradient of the tangent to the curve at that point. It is the measure of change in y with respect to x. The gradient function of y is equal to x raised to power n. So to find the gradient of a straight line, we have change in y over change in x. Change in y here is 2 and change in x is 1. The gradient of a straight line is constant. If we change the values of y and x, the gradient remains the same, 2. How about a curve like this one? Y is equal to x squared. We said the gradient of a curve at any point is the gradient of the tangent at that point. So here's a tangent to the curve at the point x is equal to 1. We can move the tangent to several points on the curve and you will notice the gradient is changing. It is not constant for a curve, but is different for different values of x. So if you wanted to know the gradient of a curve at a point, do you always have to draw the tangent? No, not really. Fortunately, there is a way of working out the gradient without having to draw the tangent. You can see that the gradient of the curve at point x is equal to 1 is 2, and that's the gradient of the tangent, that is if you take these 2 points. Let's think of this gradient in another way. If you get another point, say x is equal to 2, and connect them with a straight line, you will get a line with a gradient of 3. If you move this point closer to this other point, the gradient of its line gets closer and closer to our gradient 2. If we zoom in on this point and continue moving the second point closer and closer, that red line is getting closer to the tangent line, the blue line. If we zoom back out, we now see the gradient is really close to that of the tangent. So let's see if we can come up with a general argument. We have this curve y is equal to x squared, and down here we choose a point A. Let's say it's x units from the origin on the x-axis. The coordinates of A will be xy. But then, in this curve, y is equal to x squared. So we can replace y in that coordinate with x squared. So the coordinates of point A will be x squared. That's just replacing y with x squared. Hope you can see that. Now we introduce a small change in the x-axis. Let's say we move h units on the x-axis. H is very, very small, almost 0 but not quite. We call it a small change. So our new point will have the x-coordinate as x plus h. What will be the corresponding y-coordinate on the graph? We move up the graph, let's call this point B and try and get the coordinate. The x-coordinate is x plus h, that we already know. How about y? The curve has equation y is equal to x squared. So for every value of x, to get the corresponding value of y, we square the x value. So we shall have x plus h squared. And so the coordinates of point B is x plus h squared. We join the 2 points and then get the gradient of the straight line. Gradient is change in y over change in x, y2 minus y1 over x2 minus x1. In this case, we subtract the coordinates of B minus those of A. We shall have x plus h squared, that is y2, minus x squared, that is y1, over x plus h minus x. If we expand the numerator, we shall have x squared plus 2hx plus h squared minus x squared over x plus h minus x. In the numerator, x squared minus x squared will give us 0. In the denominator, x minus x is 0. So we remain with 2hx plus h squared over h. We factorize h in the numerator, and we shall have h into 2x plus h over h, and the h will cancel out, and we get 2x plus h. Now, as point B comes closer and closer to point A as we did, h becomes smaller and smaller. That is, it approaches 0. It is so small we can ignore it and replace it with 0. So we have 2x plus h becoming 2x. This is called the gradient function of the curve y is equal to x squared. Now, suppose we had a curve of y is equal to x cubed. We choose a point A with the x coordinates being x. Because the curve is of the function y is equal to x cubed, then the y coordinate will be x cubed. And so A will have coordinates x cubed. We add a very small increase to x so that we shall have x plus h. And therefore the point on the curve will have the x coordinate as x plus h. Again, because the curve is y is equal to x cubed, we cube the values of x to get the corresponding values of y. So the y coordinate will be x plus h cubed. And so the coordinates of B will be x plus h cubed. We join A to B and find the gradient. Change in y over change in x, that is y2 minus y1 over x2 minus x1. X plus h cubed minus x cubed over x plus h minus x. Expanding the numerator, we shall have x cubed plus 3h squared x plus 3hx squared minus x cubed over x plus h minus x. X cubed subtracts x cubed to give us 0. In the denominator, x minus x is 0. So we remain with 3h squared x plus 3hx squared over h. Factorize h in the numerator, shall have h into 3hx plus 3x squared over h. Cancel h out and we remain with 3hx plus 3x squared. Again, as B approaches A, h becomes smaller and smaller. It can be ignored and replaced with 0. And so we shall have 3hx plus 3x squared becoming 3x squared. This is the gradient function of y is equal to x cubed. If you keep increasing the power of x to say y is equal to x raised to power 4, you will have the gradient function of 4x to power 3. Y is equal to x raised to power 5, you shall have 5x raised to power 4. Y is equal to x raised to power 6, you shall have 6x raised to power 5. Y is equal to x raised to power 7, you shall have the gradient function 7x raised to power 6. If you look at the gradient functions, they show some familiar trends. In general, the gradient function of y is equal to x raised to power n is given as n times x raised to power n minus 1. And so the gradient function of y is equal to x raised to power 10 will be 10x raised to power 9. The gradient functions help us to calculate the gradient of curves at any point by simply substituting the value of the x coordinate in the gradient function. The y coordinate is not important. For example, find the gradient of the curve y is equal to x to power 4 at 0.35. First, find the gradient function of y is equal to x raised to power 4, and that will be 4x raised to power 3. The x coordinate of the point is 3, so we substitute x in the gradient function, and we shall have 4 times 3 raised to power 3, giving us 108. Next, gradient function of y is equal to ax raised to power n. Now, this is very simple. Consider y is equal to 2x cubed. This is the same as 2 times x raised to power 3. We find the gradient function of x raised to power 3 separately and then multiply by 2. The gradient function of x raised to power 3 is 3x squared. We multiply that by 2 and we shall get 6x squared. A half x raised to power 4 is equal to a half times x raised to power 4. Gradient function of x raised to power 4 is 4x cubed times a half gives us 2x raised to power 3. How about y is equal to x? This is the same as y is equal to x raised to power 1. The gradient function will be 1 times x raised to power 0. X raised to power 0 is 1, and therefore the gradient function will be 1. How about y is equal to 3? This is the same as y is equal to 3x raised to power 0, because x raised to power 0 is 1. And therefore 0 times 3 is 0, so the gradient function is equal to 0. In general, the gradient function of a constant is 0. Next, the derivative of a polynomial. Now, a polynomial is simply an expression with terms that have different powers of x. For example, 2x cubed plus 4x squared minus 2x plus 5 is a polynomial. To obtain the gradient function, we simply get the gradient function of each term separately and then retain the signs. So in our case, the gradient function of 2x cubed will be 6x squared plus gradient function of 4x squared will be 8x minus the gradient function of 2x is 2, the gradient function of 5 is 0, and so we shall have 6x squared plus 8x minus 2. 4x minus 3x cubed plus a half x raised to power 4. Gradient function of 4x is 4 minus gradient function of 3x cubed is 9x squared plus gradient function of a half x to power 4 is 2x cubed. Simple as that. When the function contains a numerator and a denominator, it is good to factorize first. For example, x cubed minus 25x over x plus 5. If we factorize the numerator, we shall have x into x squared minus 25 over x plus 5. X squared minus 25 is a difference of two squares that can be written as x squared minus 5 squared. The difference of two squares is the product of the sum and the difference. So x squared minus 5 squared is the same as x plus 5 times x minus 5. And now we multiply by x over x plus 5. So x plus 5 will cancel out and we remain with x squared minus 5x. And so the gradient function of that will be 2x minus 5. Next, the delta notation. Now, in our explanations, we used h to represent the small change in x. The Greek letter delta is used to indicate a small change, and so delta x means a small change in x. Delta y means a small change in y. Notice that delta x is a single entity and does not mean delta times x. If we work the gradient function of our curve, we simply replace h with delta x. So in our case, gradient AB will be delta y over delta x. That is change in y over change in x. So replacing h with delta x, we shall have x plus delta x squared minus x squared over x plus delta x minus x. Expanding that, we have x squared plus 2x delta x plus delta x squared minus x squared over delta x. Factorize delta x in the numerator, we shall have delta x into 2x plus delta x over delta x. Delta x cancels out and we remain with 2x plus delta x. As b moves closer to a, delta x approaches 0 and can be ignored, and so we shall have 2x. This process of obtaining the gradient function is called differentiation of x squared with respect to x. The gradient function is called the derivative. When delta x approaches 0, delta y over delta x becomes dy over dx, where dy over dx means the derivative of y with respect to x. If you remove y, the symbol d over dx denotes derivative with respect to x of. And so if you have x cubed, then we say the derivative of x cubed with respect to x. That is written as d over dx of x cubed, and then we differentiate x cubed. So we shall have d over dx is equal to the derivative of x cubed is 3x squared. If you had a function y is equal to x cubed, we would now say the derivative of y with respect to x. And the reason we say that is because now x cubed is y. And so where we said the derivative of x cubed, we now put y instead. And so we shall have dy over dx is equal to d over dx of x cubed. So dy over dx will be equal to 3x squared. When you have a function, it's okay to go directly to dy over dx and save time. For example, y is equal to 2x cubed plus 3x squared minus 4x plus 5. We simply say dy over dx, that is the derivative of y with respect to x, will be equal to the derivative of 2x cubed will be 6x squared plus derivative of 3x squared will be 6x minus derivative of 4x will be 4, and derivative of y is 0. For example, find the gradient of the curve y is equal to x squared plus 5x minus 7 at point x is equal to 2. In such cases, we've seen that you find the gradient function, that is differentiate, and just substitute the value of x in the gradient function. And so dy over dx will be equal to, the derivative of that function will be 2x plus 5. We have x is equal to 2, so we just substitute x in the gradient function. 2 times 2 plus 5 will give us 9. And so the gradient of the curve y is equal to x squared plus 5x minus 7 at point x is equal to 2 is 9. Sometimes the examiner may give you the y coordinate and ask you to find the gradient. You must remember in the gradient function only the x coordinate is useful. So before differentiating, you must find the corresponding x coordinate from the equation of the curve and not from the gradient function. For example, find the gradient of the curve y is equal to x squared plus x minus 6 when y is equal to 0. So we find the x coordinate at the point y is equal to 0. This is a quadratic graph, and so we expect two values of x. Substitute y with 0, we shall have x squared plus x minus 6 is equal to 0. I've just shifted y. We solve the quadratic equation. That will give us x squared plus 3x minus 2x minus 6 is equal to 0. Factorize x into x plus 3 minus 2 into x plus 3 is 0. Collect the terms. X minus 2 times x plus 3 is equal to 0. So we shall find x is equal to 2 and x is equal to minus 3. Gradient function dy over dx is equal to, the gradient function of that will be 2x plus 1. By now you know how to do it. Substitute the first value of x2. 2 times 2 plus 1 is equal to 5. And so the gradient of the curve y is equal to x squared plus x minus 6 when x is 2 is 5. Substitute now negative 3. 2 times minus 3 plus 1 will give us minus 5. And so the gradient of the curve y is equal to x squared plus x minus 6 at the point x is negative 3 is minus 5. It's very important to see that we first get the corresponding x coordinate using the equation of the curve and not the gradient function. That is a common mistake by students. Now, suppose we have the equation of the curve and the gradient, and you are supposed to find the coordinates. For example, find the coordinates of the point on the curve y is equal to x squared minus 5x plus 6 at which the gradient is 5. In this case, what we do is simply find the gradient function. We equate it to the gradient and solve for x. From there, we find the corresponding value of y. And so dy over dx will be equal to 2x minus 5. We know the gradient is 5, and so we equate that to the gradient function. 2x minus 5 is equal to 5. 2x is 10, x is 5. And so we know at the point where gradient is 5, the x coordinate is 5. Now we find the corresponding value of y at that point where x is 5. Notice that dy over dx is what is 2x minus 5. It is not y. Y is equal to x squared minus 5x plus 6. So to get the corresponding value of y, we substitute the value of x into the equation that contains y. So we shall have y is equal to 5 squared minus 5 times 5 plus 6. Y is equal to 25 minus 25 plus 6, and y is equal to 6. So the coordinate of that point will be 5, 6. X is 5 and y is 6. Next, equations of tangents and normals. Now, the tangents and the normals are straight lines, and so their equations are in the form y is equal to mx plus c, the equations of straight lines. We know what a tangent is by now. A normal is a straight line that is perpendicular to the tangent at the point of contact with the curve. So the first clue is that the normal and the tangent have the same coordinates at the point of contact. Second clue, for perpendicular lines, gradient 1 times gradient 2 is equal to negative 1. Remember, the gradient of the tangent is equal to the gradient of the curve at the point of contact. Let's take an example. Find the equation of the tangent and the normal to the curve y is equal to x squared minus 5x plus 6 at the point x is equal to 0. To get the equation of a line, we need the gradient and a point. Gradient of the tangent is equal to the gradient of the curve at the point of contact, and so we find the gradient function first. dy over dx, we derive that function, x squared minus 5x plus 6. If we differentiate that, we get 2x minus 5. So the gradient at point x is equal to 0. We simply substitute 0 in the gradient function. 2x times 0 minus 5 will give us minus 5. So that is the gradient of the tangent. Now we know the x coordinate is 0. So we need to find the corresponding value of y at that point where x is 0 using the equation of the curve. Y is equal to x squared minus 5x plus 6. We substitute 0 for x, so we shall have y is equal to 0 squared minus 5 times 0 plus 6, and y is 6. So the point of contact is 0, 6. Equation of the tangent. Now we have the gradient and a point. Gradient is negative 5 and the point is 0, 6. Now we find the equation of the straight line. We find an arbitrary point xy, and then we do y2 minus y1 over x2 minus x1 and equate that to the gradient. So y minus 6 over x minus 0 is equal to negative 5 over 1. Cross multiplication, y minus 6 is equal to minus 5x. Y is equal to minus 5x plus 6. That is the equation of the tangent to the curve at the point x is equal to 0 or at point 0, 6. Equation of the normal. We have a point 0, 6. We said the normal and the tangent have a common point at the point of contact. Gradient 1 times gradient 2 is equal to negative 1. Gradient 1 we have is negative 5, so gradient 2 must be 1 over 5. Arbitrary point xy and our point 0, 6, equate that to the gradient. Y minus 6 over x minus 0 is equal to 1 over 5. Cross multiplication, 5y minus 30 is equal to x. 5y is equal to x plus 30. Y is equal to 1 over 5x plus 6. That is the equation of the normal to the curve at that point 0, 6. Another example. Find the coordinates of the point on the curve y is equal to x squared minus 4x plus 2, where the tangent is parallel to the line y is equal to 2x minus 3. We have a line parallel to the tangent to our curve. It means we can get the gradient of our tangent. Recall that for parallel lines, gradient 1 is equal to gradient 2. For the line y is equal to 2x minus 3, the gradient is 2. So the gradient of our tangent is 2 as well. So the whole story has now reduced to finding the coordinates of the point on our curve where the gradient is 2. Let's start with the x coordinate, and we need the gradient function first. dy over dx for our curve will be 2x minus 4. That is the gradient function, and we know the gradient is 2, so we find the x coordinate at that point. So we have 2x minus 4, we equate to the gradient 2. 2x is equal to 6, x is equal to 3. So the x coordinate at the point where the gradient is 2, we have found to be 3. Now we find the y coordinate. We substitute 3 for x in the equation of the curve. Y is equal to 3 squared minus 4 times 3 plus 2. That gives us y is equal to -1. And so the point is 3, -1. Next, stationary points. A stationary point on a curve is the point at which the gradient is 0. Therefore, at the stationary point, dy over dx is equal to 0. At such a point, the tangent to the curve is parallel to the x-axis. The stationary points of a curve are in 3 categories depending on the shape of the curve in the immediate neighborhood of the points. If the stationary point is a crest, then it is called a maximum stationary point. A and D are maximum stationary points. If it is a trough, it is a minimum stationary point. C is a minimum stationary point. When the point is neither a crest nor a trough, but nonetheless a stationary point, it is called a point of inflection. B is a point of inflection. You must realize that when the curve is inclined in the right side, the gradient is positive. If inclined towards the left, it is negative. So in a maximum stationary point, the gradient changes from positive to 0 and then to negative. It is symbolically represented as this. In a minimum stationary point, the gradient changes from negative to 0 and then to positive. It is represented as this. For a point of inflection, the gradient may change from negative to 0 and then to negative again, or from positive to 0 and then to positive once again. Let's take an example. Find the coordinates of the stationary point on the curve y is equal to x squared minus 4x. We now know that at a stationary point, dy over dx is equal to 0. So we find dy over dx and equate it to 0, and then we solve for x. After that, we find the corresponding value of y. So dy over dx for our case will be 2x minus 4. We equate that to 0. 2x minus 4 is equal to 0. 2x is equal to 4 and x is equal to 2. Now we substitute that in the equation of the curve to get the y coordinate. Y is equal to 2 squared minus 4 times 2. That gives us y is equal to minus 4, and so the stationary point is 2 minus 4. But now, the calculation tells us the stationary point, but does not tell us if it is minimum, maximum, or even a point of inflection. To know the nature of the stationary point, we test the gradient of the neighboring points, left and right. That way, we will know how the gradient changes. We have the x-coordinate of 2. We test the gradient for x is equal to 1 and x is equal to 3. That is the neighborhood of x is equal to 2. For x is equal to 1, we have dy over dx is equal to 2x minus 4. When x is 1, gradient will be 2 times 1 minus 4, and that is minus 2. The gradient to the left is negative. Gradient at the stationary point, that is x is equal to 2, is 0. When x is equal to 3, the gradient will be, substitute 3 into the gradient function. 2 times 3 minus 4 gives us 2. So the gradient to the right is positive. The gradient changes from negative to 0 and then to positive. So that looks like this. It is a minimum stationary point. Another example, find the coordinates and the nature of the stationary points for the curve y is equal to x cubed minus 12x plus 2. We get the gradient function and equate it to 0. dy over dx is equal to, that will give us 3x squared minus 12. The stationary point dy over dx will be 0. So we have 3x squared minus 12 is equal to 0. We divide everything by 3 and we shall get x squared minus 4 is equal to 0. X squared is 4 and x is plus or minus 2. So we have two stationary points. X is equal to 2 and x is equal to minus 2. Let's first find the y coordinates. So for x is equal to 2, what will be y? We substitute y is equal to 2 cubed minus 12 times 2 plus 2, and that gives us minus 14. So that stationary point has coordinates 2 minus 14. Let's call it A. When x is negative 2, what will be the y coordinate? Substitute y is equal to minus 2 cubed minus 12 times minus 2 plus 2 will give us 18. And so the other stationary point has coordinates minus 2, 18. Let's call it B. So let's find the nature of the stationary points, and we start with A. At A, x is 2, and the gradient at a stationary point is 0. So we test the neighborhood of x is equal to 2. We test x is equal to 1 and x is equal to 3. When x is equal to 1, from the gradient function, gradient will be 3 times 1 squared minus 12 will give us minus 9. That is negative. When x is equal to 3, gradient will be, we are substituting in the gradient function. That will give us 3 times 3 squared minus 12, giving us 15. So the gradient changes from negative to 0 and then to positive. This is a minimum stationary point. So point A is a minimum stationary point, and we represent it with this symbol. Point B, what is the nature of the stationary point? The coordinate of x at the stationary point is x is equal to minus 2, and at that point gradient is 0. We test the neighborhood of x is equal to negative 2. We shall test x is equal to negative 3 and x is equal to negative 1. Notice that x is equal to negative 3 is on the left. X is equal to negative 1 is on the right of the stationary point. When x is equal to negative 3, the gradient will be 3 into minus 3 squared minus 12. That gives us 15 positive. When x is equal to negative 1, substitute in the gradient function. That will give us 3 into minus 1 squared minus 12. That will give us minus 9, negative. So the gradient changes from positive to 0 and then to negative. It is a maximum stationary point. Next, sketching curves. A sketch represents the general view of the actual curve. In sketching curves, we are only interested in the general shape and features. We need the x and y intercepts and the coordinates and nature of the stationary points. For example, sketch the curve y is equal to x squared plus x minus 6. We first get the intercepts. Start with the y-intercept. The y-intercept occurs when x is equal to 0. So we substitute x with 0 in the equation of the curve to find the corresponding value of y. So y is equal to 0 squared plus 0 minus 6. That gives us minus 6. So the y-intercept is at 0, negative 6. X-intercept. The x-intercept occurs when y is equal to 0. So we substitute 0 in place of y and solve for x. This is a quadratic function and we expect two values of x. X squared plus x minus 6 is equal to 0. Find two numbers such that when you multiply them you get negative 6, and when you add them you get positive 1. Those numbers are 3 and negative 2. Rewrite that. X squared plus 3x minus 2x minus 6 is equal to 0. Factorize. X into x plus 3 minus 2 into x plus 3 is equal to 0. X minus 2 times x plus 3 is equal to 0. If you find that, you get x is equal to 2 and x is equal to minus 3. So x-intercepts, that is 2, 0 and negative 3, 0. Stationary point, dy over dx is equal to 0. So the gradient function for that will be 2x plus 1. 2x plus 1 is equal to 0 and x is equal to minus a half. At the stationary point, x is equal to minus a half. What will be the y-coordinate? We substitute that into the equation of the curve. Y is equal to minus a half squared plus minus a half minus 6. We work that out, we get y is equal to minus 6 and a quarter. So the stationary point is at minus a half minus 6 and 1 over 4. Nature of the curve. When x is equal to minus a half, the gradient will be 0. We test the gradient at the neighborhood. We test x is equal to minus 1 and x is equal to 0. When x is equal to minus 1, gradient will be 2 times minus 1 plus 1, giving us minus 1, so it's negative. When x is 0, gradient will be 2 times 0 plus 1, giving us 1. That is positive. And so the gradient changes from negative to 0, then to positive. It is a minimum stationary point. With all these details, we can now sketch our curve and it will appear as this. Lastly, differentiation kinematics. Now, differentiation can be used to determine and solve equations for distance, velocity and acceleration. These quantities are called kinematics when the force causing them is ignored. We start with velocity. Consider a moving body such that its distance s meters after time t seconds is given by the equation s is equal to 5t plus 10. If you plot the graph of distance against time for this equation, it will be a straight line. In Form 2, we saw that the gradient of a distance time graph gives the velocity of the body. For this equation, s is equal to 5t plus 10. If you relate it with y is equal to mx plus c, the gradient will be 5. Suppose we differentiated the equation instead. We differentiate distance with respect to time, ds over dt, it will give us 5, the same gradient. In general, in kinematics, when we differentiate the expression for distance, we obtain the velocity function. For example, the distance s covered by a body in time t seconds is given by s is equal to 3t squared plus 4t minus 5. Find the velocity of the body after 4 seconds. We obtain the velocity function by differentiating the distance function. So v, the velocity, is equal to ds over dt, and that will give us 6t plus 4. What is v at t is equal to 4 seconds? We simply substitute that. V is equal to 6 times 4 plus 4, and that is equal to 28 meters per second. Acceleration. Acceleration is the rate of change of velocity. Again, we know that the gradient of a velocity time graph gives us the acceleration. To obtain the acceleration function, we differentiate the velocity function. And so acceleration is equal to dv over dt. For example, a body moves in a straight line such that its distance s in meters after time t seconds is given by s is equal to 2t cubed plus 4t squared minus 4t. Find A, the time when the body is momentarily at rest, B, velocity after 3 seconds, and C, acceleration after 4 seconds. In the solution, A, when the body is at rest, it means the velocity is 0. So we get the velocity function first. V, velocity, is equal to ds over dt, which is equal to, when we differentiate that, 3t squared plus 4t minus 4. We equate that to 0. 3t squared plus 4t minus 4 is equal to 0. Two numbers, when you add, you get 4. When you multiply, you get minus 12. Those numbers are minus 6 and 2. We rewrite that 3t squared plus 6t minus 2t minus 4 is equal to 0. Factorize 3t into t plus 2 minus 2 into t plus 2 is equal to 0. 3t minus 2 times t plus 2 is equal to 0. 3t minus 2 is equal to 0. We'll find t will be equal to 2 over 3 seconds. For the other one, t plus 2 is equal to 0 and t is equal to minus 2. That is not possible because time cannot be negative, so we ignore that. Velocity at time is equal to 3 seconds. V is equal to, we simply substitute that into the velocity function. 3 times 3 squared plus 4 times 3 minus 4 will give us 89 meters per second. Finally, acceleration will be given by dv over dt, which is equal to, when we differentiate the velocity function, we get 6t plus 4. So when t is equal to 4, acceleration will be 6 times 4 plus 4. That gives us 28 meters per second squared.
And so you can go on and learn math. You may need tutorials, you may need tutors, etc., to get your foundation solid so that you can build the next course on it. But math is not so complicated that most people can't learn high school math and certainly the introductory courses in university. If you want to go on and major in math or do honors in math or do a career in math, you really do need to be good at it. But I think too many people stop out too soon because they've had bad experiences. I think math teachers have a lot of responsibility for that. We haven't taught it so well. We haven't provided the resources that people need. And so I think if you need help, you need to get it, and you need to get it early. And you need to work at it.